long-awaited return of your favorite YouTuber. We have a very nice snowstorm going on outside, and I've already recorded this video twice, so maybe third time's the charm. But we're going through pressure and Pascal's law today. Okay, so first we're going to start off with just, oh, that is not the right one. We're going to start off with just some definitions of pressure. Okay, you should know that pressure is equal to force divided by area. Okay, so again, in this formula, P stands for pressure, F stands for force stands for F, yes, and area stands for A stands for area, all right? So we're gonna start with force here. Force is a push or a pull, okay? So if you're pushing on something or you are pulling on something, okay? This guy's getting his exercise in. Those are sweat drops, by the way. Please don't laugh at my drawings. I've been laughed at twice already today. But a force is a push or a pull, okay? Push or pull, and usually it causes movement. That causes movement. Okay. If you are wondering why you don't fall through the floor, it's because forces have opposites. So if you're not actively moving, or if you're pushing something and it's not actively moving, it's because there's actually another force that is canceling that out. Okay? So if the force doesn't have an opposition, it's going to cause movement. All right. The next thing you need to know about force is that it's measured in newtons. It's a capital N, okay? And it's named after a certain scientist that may or may not have actually discovered gravity first. There are some disputes about that. Okay, so again, push or pull, measured in newtons. Easy peasy. Next, we have area, okay? We know that area is how much 2D space something takes up, and you measure it in something squared, right? So you could think centimeters squared, you could think meters squared. In terms of pressure, you have to use meters squared, okay? And that is because pressure is technically measured in newtons per meter squared. But we are scientists, and scientists like simplicity. So we don't write this. We represent newtons per meter squared as pascals. Okay, so it's written as PA, kind of like centimeters is shortened to cm, but the actual word is pascals. And again, it's named after another scientist who was responsible for a lot of cool things, and we will discuss Pascal's law in a little bit. Okay, so pressure again is, if it's newtons divided by meters squared, it's really the amount of force exerted or put on a certain area. Okay? So you can push and pull as much as you want, but pressure only looks at where that force is put on. Okay, so for example, in this drawing here, right, this person is pushing, the area that they're pushing is only this little bit here. And the area that they're pulling, again, is only this little bit here. So pressure is very, very affected by area. Just keep that in mind. Okay, so now we know what area is, now we know what force is, now we know what pressure is. So let's talk about some examples of pressure. So the first example we looked at was if you are using a hammer to try and dent a piece of wood, right? So here's my hammer, okay? And when you are swinging a hammer, you are swinging down with a certain force, right? It's going to be a push. You're pushing this hammer down, okay? Now this hammer is going to smash into this piece of wood, but it's probably not going to do very much to it. It might just give it a dent. Okay? When this hammer hits the piece of wood, it is only contacting the wood with the part you're hitting. So there's this much force, there's that much area. Okay? So the pressure that this hammer is putting on this piece of wood is going to be equal to this force divided by this area. Okay? So I'm going to make up some numbers just to give you an example of what this would look like. So let's just say the force is 100 newtons. Okay, 100's an easy, nice number. 100 newtons. Okay, and we're going to divide it by, this is quite small, so maybe I'll say it's 0.05 meters squared. Okay, that's probably already too big, but anyway, you get the idea. It's not that big. So if we divide these two, we will get the pressure. So 100 divided by 0.05 should be, please check my math, should be about 2,000 pascals. I think so. If not, please forgive me. So yeah, this is the amount of pressure that this hammer is putting on to this piece of wood. Okay, so that's that. Now the other example we looked at was, what if you used a hammer, but instead of having the hammer directly hit, you're using a nail. Okay, so this is the same sized hammer, all right, with the same amount of force, the same bad drawing, but now the only difference is that this force is going here, it's going onto the hammer, the hammer's going onto the nail, and then the nail is hitting the piece of wood with only this much area. So do you see how much smaller that is? Oh my gosh, also, I just discovered I could use more colors. I will try that in another video. But again, certain amount of force, same force, okay? Much smaller area. So I'm going to show you the math for that part. So again, force divided by area. Force, this force is still 100 newtons, divided by area. This time the area is much smaller, so I'm going to choose a smaller number, maybe 0.0001 centimeters squared, okay? I should have put A there. I'm going to fix that. Give me 1 second, so it should be A. I'm going to put the number here. Okay, 0.001 meters squared, okay? So again, same force, different area. The area is smaller. So what happens to the math, right? This time, if I do 100 divided by 0.0001, I should get 3, 4, 5, 6. I should get 1 million pascals. Okay? And so do you see how, with the same amount of force, depending on how big that area is, I can make way different amounts of pressure. Okay? And this is why, if you hit a hammer, if you hit a piece of wood with a hammer, you might just dent it with 2,000 pascals, right? But if you hit a hammer with a nail, same force, but now suddenly this nail's area is much smaller, you have almost, what is that, like 5,000 times more pressure? And so the nail is going to be the thing that cracks the wood open. But here it's just going to get a little dent. Okay, so that's the magic of pressure. That's why pressure is different from just force. Force is just the push or pull. Pressure is on what area, right? On a certain area. On what area is that force put on? Okay, so that's part one. That's pressure. Next, we're going to go to Pascal's law. Okay. Bloop. Okay, so I'm going to just keep some important math up here. So again, pressure equals force divided by area. We're going to keep that in mind. Okay, so next, Pascal's law. Could you guess who made this law? I think it's Pythagoras. All right, anyway, so Pascal's law has a very wordy definition. Okay. I cannot even remember the wordy definition. So if I go look it up right now, let's see if I get confused. And you know where you can find this? You can find this on your Google Classroom under Lesson 8, Pressure. So I'm going to do that. I'm going to pull that up. And I'm going to see exactly what it says. Lesson 8, Pressure. Um, it's a force per unit of area. Oh wait, sorry, I was looking at Pascal's law. Haha, Pascal's law. Okay, so Pascal's law, thank you for listening. I should put some elevator music in there. It is the pressure exerted on a fluid, that's an F, I'm sorry, is transferred uniformly throughout the fluid. Okay, so again, that's an F, I'm really sorry, but this is the definition. Now, does this make any sense? Many people will say, I have no idea what that is. So first we're going to break this down, and then I want you to focus on explaining the diagram instead of just memorizing this and then not understanding what it means, okay? So first, pressure exerted means like put on, right? Pressure like put on a fluid is transferred uniformly. Uniformly means the same, right? The same throughout the fluid. Okay, what does that look like? So we're going to revisit this little picture here. Okay, we have a fluid in this container. It is capped off, okay, so it's sealed shut. And we have a certain amount of pressure pushing down on this. How do we know how much pressure? Well, you had to start off with a certain force, right? And that force is being exerted on this area. So again, with our force divided by area, we get a certain pressure. Okay. All right. So now this pressure is going to be exerted on this fluid from here, right? And it's transferred uniformly the same throughout the fluid. So that means there's going to be an equal pressure here. There's an equal pressure here, an equal pressure here, and so forth. Because remember, pressure is force on a certain amount of area, right? So there's lots of area here. So we're not counting, we're not adding these up. We're just saying for every area that is this much, right, there's going to be a certain amount of force. Okay, so the pressure again is the same. This pressure is not any smaller than this. This pressure is not smaller than this. This pressure is not smaller than this. It's all equal. So if I gave a number example, right? Oh my goodness. Let's just say we had 20 pascals here. This would also be 20 pascals. This would also be 20 pascals. This would be 20 pascals. This would be 20 pascals. This would be 20 pascals. We get the idea, right? We're not dividing the pressure at all. The pressure stays the same. But now because there's more area, there's the same pressure everywhere. Okay, so that's exactly what this means. Now let's bring it over to the car example. This kind of confused a lot of people in class, so just think of it as the same way. If the words confuse you, focus on explaining the diagram. All right, so same thing. We're going to start with a platform here. We're going to start with a seal here, and we're going to put a car on this side. So, do you know how much a car weighs? I'll give you a hint, it's a lot. I don't know how much it is exactly, but that's something that Google could tell you right about now. So I'm going to have a little stickman guy, okay? He's getting swole over here. So he's putting a certain amount of weight, a certain amount of force on this platform over here. No matter what you lift, it's probably going to be less than an entire car. So again, there's a certain amount of force here. The force is on a certain amount of area, and that means we create a certain amount of pressure. Okay? So now this time I'm going to make up another number. Let's just say our pressure. Actually, let's make up our forces first. So let's say our force is 100 newtons. Okay. Let's just say our area is 0.5 meters squared. Okay. And so if we divide it, we get pressure. So our pressure is going to be equal to 100 divided by 0.5. So it's going to be 200 watts. What's the unit again? I feel like Dora the Explorer. What's the unit? It's pascals. Okay, so just remember it's measured in pascals. So we have 200 pascals of pressure here. So how much pressure are we going to have here? Also 200. I've never felt so much like Dora the Explorer. So again, remember, everywhere uniformly the same throughout the fluid, we're going to be having the same pressure no matter where you are. Okay? So pressure never changes. I'm just going to finish this diagram. Okay? All right. So cool. Next, okay? We said that pressure will not change no matter what. So over here, the pressure still 200 pascals. But the area that this pressure is being exerted on is different, right? In total, let's say if we take that, I'm going to see how many times that fits here. So 1, 2, 3, 4, 5. We have maybe 5 times the pressure here. So I'm going to say that our area is like 2.5 meters squared. Okay, bigger area. Then what that means is we have to have something divided by 2.5 to get 200 pascals, right? And so you don't have to worry about how to get this math right now, but the actual force is going to be much bigger. If you want to know exactly how to get it, you just need to do 200 times 2.5. Do I have the mental math chops? Am I a mental math champion? Let's find out. 1, 2. I'm not a mental math champion. Oh no. Is this 500? It's 500. Maybe I am a mental math champion. Okay. So anyway, the newtons are going to be 500. Okay, so if you do 500 divided by 2.5, that equals 200 pascals. So the pressure stayed the same. The area was bigger. And so now, by starting off with this small force, we were able to push up on this car with a force that is 5 times more than what we started with. Okay? We didn't need 500 newtons to lift the 500 newton car. We only had to start with 100 newtons. So that is the beauty of Pascal's law. Okay? You can use pressure, and you can increase the pressure by making the area small in order to transfer that pressure somewhere else. And then, even though the pressure is the same, the area is bigger, so the force is also much bigger. Ladies and gentlemen, there we go. Have a lovely evening. Stay warm. If only it actually stopped when I stopped it. That would have been a great ending.